Hey everyone, thanks for staying so late in the day to listen to this talk. I'm going to be talking today about this concept of slow or fast and slow interoperability. A little bit about myself. My name is Bo. I'm a technical co-founder at Polymer. Personal background is in database engineering. I worked at a few different startups on the core database team before transitioning into Web3. So I want to talk about this concept of fast and slow systems. As a generalization here, fast and slow systems are systems that are fast in the majority of the time and slow a smaller percentage of the time. The two systems kind of counterbalance each other, making them responsive while also retaining the ability to handle complexity. Neither fast nor slow system in this context works well in isolation. And I'm going to talk about some specific examples of this. So a lot of you may have read this book. Daniel Kahneman's book, Thinking Fast and Slow, talks about two forms of thinking. Fast thinking and slow thinking, which aid in our decision-making process. For fast thinking, it happens automatically. It's great for everyday tasks, requires little to no effort. Some examples of this may be choosing a t-shirt in the morning or recognizing a friend in a crowd. On the other hand, you have slow thinking, which is methodical, analytical, and deliberate. This thinking is great for complex computations and decision-making and requires high effort. Some examples of this include deciding on a career direction, coming up with an investment thesis, and so on. Another example is at the checkout counter. If you go to a store, generally you're able to check out with your goods immediately and leave. This fast checkout process is enabled by the sales terminal recording a sale immediately, while a slow settlement process batches these orders and submits them to the Visa network at the end of the day for processing. This is another example of a fast and slow system that enables good user-facing experience while also retaining the ability to have consistent accounting at the end of the day. Intents are another example. Intents give us fast transfers where solvers immediately fill user orders, while the settlement process, where the solvers get repaid, as in the case of a cross, happens within 1 to 2 hours. Without this fast and slow system, the value transfer for L1 native assets on Ethereum would be painfully slow, as it would have to go through the native bridge. The last example I want to talk about is this concept of fast and slow interoperability. At a very high level, what this means is you allow messaging to happen fast without waiting for the L1 in the fast path, while having a slow settlement process during which messages are validated. Superchain native interop is an example of this. We'll get more into detail later on in the presentation, as well as go over additional examples of this. So all the systems that we talked about so far embody this concept of eventual consistency. Eventually consistent systems generally follow the pattern of having some upfront guarantee that's a little bit weaker during the fast path, which eventually converts to a much stronger guarantee during the slow path. In database land, there's many examples of this, including high-scale database systems that allow users to trade off performance for consistency. In these models, these databases will enable high throughput, fast writes, while delaying reads or consistent reads to a much later period. Now, how is eventual consistency achieved in rollup interop? To understand this concept, I want to first talk about the idea of edge formation and validation. Let's define what an edge is first. An edge in this graph is considered created when a cross-chain message is sent from an origin to a destination. An edge link represents an unvalidated input to the destination with a validated output on the source. These edges can then be either optimistically or pessimistically validated. For example, in the ag layer, edges are pessimistically validated using zero-knowledge proofs. And in Optimism's superchain native interop, these edges are optimistically validated with no proof required upfront. With optimistic edge validation and weaker pessimistic validation, we get this eventually consistent accounting model where we allow for fast UX or fast messaging that can occur between milliseconds to seconds latency with a weaker guarantee that eventually converts to a much stronger guarantee at settlement time, which happens with minutes to days latency. So there's two forms of settlement time validation that I want to talk about. We have shared and chained validation. Let's talk about shared first. So at a high level, shared settlement time validation generally involves a number of rollups that settle to the same layer 1 bridge. In this model, we execute all of the rollup state transitions and produce a single list of source and target nodes. These source and target nodes represent edges in the graph. Validated outputs on the source to unvalidated inputs on the destination or the target nodes. The validated outputs are green and the unvalidated inputs are red. And what the algorithm would do at a high level is iterate through all the target nodes and look for any that are missing a source node. This is now marked as an invalid edge in the graph, which at settlement time, we end up reverting all these edges, invalid edges, which is implementation dependent, depending on the protocol. Chained settlement or chain validation works where you have a number of layer 1 bridge contracts. Each rollup settles independently. However, the final settlement of that rollup is pending the validation of all unvalidated edges, meaning that you would execute each rollup individually, produce multiple lists of source and target nodes, and the rollups would get together and check the edges themselves across all these lists and ensure that there are none that have missing links. And for any target nodes that have that do not have a source node, you would then revert all these invalid edges once again. So regardless of how the rollup settles, rollups that settle together form a rollup cluster. And I'm defining a rollup cluster specifically in this case because of the trust model deployed by the property of being able to settle together. Rollups in these clusters then inherently trust each other in the fast path, meaning that each rollup creates systemic risk in the cluster itself. So for example, the superchain native interop for their initial superchain dependency set, every rollup in the dependency set represents systemic risk in the cluster, and all rollups in that cluster trust each other in fast-pass messaging. And at settlement time, invalid edges are eventually pruned, resulting in eventually consistent accounting within the cluster itself. So what are some problems with this fast and slow design? The first problem I want to highlight is the issue of cascading reorgs. This happens when rollup A finds some invalid edges at settlement time, which causes rollup A to roll back, which then would cause rollup C to reorg, which then causes rollup B to reorg, and this can keep going on and on and on. And I've included an image of Cascade dishwashing soap in there to motivate the imagery here. There's an issue with off-ramping. Every single off-ramp wants to guarantee that the state transition of the rollup that they're off-ramping from, or chain that they're off-ramping from, is both valid and final. Yeah. So both of these are issues. And lastly, we have the issue of cross-cluster communication. The fast and slow design solves interoperability within a cluster, but does not extend across different clusters. So how do we prevent cascading reorgs? The naive approach here is acknowledging that rollup A, B, and C in this model in order for rollup A to determine that its state transition function is valid, it actually would need to run a full node for rollup B and C, and vice versa. If every rollup in the cluster runs a full node for every rollup in the cluster, they can have strong pessimistic guarantees that the state transition is correct and that there will be no rollback at settlement time. This is actually the model that Superchain Native Interop deploys today. They have an OP supervisor process that's run locally to every single sequencer, and every single sequencer node also runs a full node for all connected rollups, resulting in this design here. Another issue that we need to solve is sequencer equivocation. This problem occurs when a sequencer submits an ordering to the L1 that is different from the ordering that it originally created at block production time. This means that there would be two different blocks produced at the same height by the sequencer. And the way we can prevent this is with one of two methods. We can either run the sequencer in a TE, relying on hardware level guarantees of correctness, or we can use Espresso's confirmations product, which enforces a specific ordering at settlement time, meaning that the rollup sequencer would not be able to post a different ordering as it would violate the protocol. And this is guaranteed by Espresso consensus. So how do we solve the off-ramp problem? In general, most off-ramps will run a full node for any chain that they're connected to. What this means for rollup interop is that the off-ramp is now required to run a full node for every single rollup in the rollup cluster to have full confidence that the state transition function is correct. Additionally, they would also have to wait for layer 1 finality before processing withdrawals. And this is due to contagion risk in the cluster from all the different rollups. So for the superchain, base would not only have to run the base rollup, they would have to run every other rollup in the superchain dependency set to perform this off-ramping function. Now for cross-cluster communication, we can see in the diagram that we have pre-settlement and post-settlement. In the pre-settlement path, the fast path is trusted. Unfortunately, in this model, there's no eventually consistent accounting here. The fast path will always remain trusted, regardless of if the rollups have settled or not. The other option is just to wait till the rollups have already settled before communicating. You could do this through the L1, through standards like RP 7755 and storage proofs. But the trade-off here is that it's very slow. So there's no great solution for fast cross-cluster communication. Now, what are some specific examples of this fast and slow model for interoperability? The first example I want to highlight is CIRC, Coordinated Inter-Rollup Communication. It's courtesy of Ellie at Espresso. It's one of the protocols that they've developed in-house. You have low latency messaging that happens in the fast path that's either intra or inter-block, and this happens through inbox and outbox contracts on different chains. And at settlement time, we perform a consistency check where we take the union of all inboxes and the union of all outboxes, hash those together, and make sure that they match. This also means that messages have to be delivered to make sure this consistency check passes. Another example that we mentioned at the beginning of the presentation is Superchain Native Interop. We'll dig into more details here. So in Superchain Native Interop, once again, we have low latency messaging that's possible either intra or inter-block. The messages can be any log or event. And I'll define what IM and EM is here. IM stands for an initiating message, which represents an event or log on the origin. And EM represents a pointer on the destination to an event or log on the origin. And if we scroll back a few slides here, we can see that these are the source and target nodes that I was talking about in the abstract here. At settlement time, we perform a check where every single executing message is matched to initiating message, as was the algorithm before with the source and target nodes. And EM is considered a target node, and IM is considered a source node. This consistency check in Superchain Native Interop actually happens twice. It happens once when the layer 2 is derived from the layer 1, which means that the layer 2's block is derived from L2 data that has been already published to the L1. And once again, when the state transition function is fully validated on the L1, and this is the full settlement process with the 7-day fraud window. And I put a star here because this process, it's a to-do currently, so they haven't actually spec'd out or implemented this yet. But in theory, this is how it would work. Okay, just FYI. Yeah, they'll figure it out. So Polymer also represents another model for fast and slow interoperability. In the Polymer model, Polymer is a rollup. It ingests block headers from connected rollups and allows for log or event proofs to be sent from chain to chain. This happens in the fast path. And then eventually, at settlement time, we perform the same check roughly as in superchain native interop. We have this list of source nodes and we have this list of target nodes that we match to one another to perform this consistency check. We drafted this ERC 7868 called verifiable cross rollup links to describe this process at a high level. This shared or chain settlement across rollup framework standard is generic to any rollup framework. There's 2 identifier formats in it. There's an identifier format for a log. There's an identifier format for a storage key, either of which can be used as a cross rollup link. Also, this spec is not finalized and it's not yet implemented in rollup frameworks. So the main takeaway here that I want to leave everyone with is when these fast and slow systems work together, everyone wins. You get great UX and strong guarantees at settlement time. Thank you. And if anyone wants to chat with me about any of these ERCs, any of these standards, or reach out to us to chat about cross-chain proofs, please find me on Twitter or go to our website, and we have documentation there as well. Yeah, I think so. From my perspective, Circ is a messaging protocol. What I'm talking about here isn't a messaging protocol. It's just a proof protocol, like lower level. How do you verify? How do you actually perform the consistency check? But yeah, it should be technically it should be able to work with like any messaging protocol, Circ, IBC, or otherwise.